Hello everyone, we're going to run through the equation for a sheet for the Physics 202 exam and go over what is located where so we know. And now, some of these equations are unnecessary, some of them we need. He writes things in different ways than I do, which is fine. Now up here, this is a photoelectric effect written kind of strangely to me. I'm used to the photoelectric effect being Ke equals Hf minus the work function. And that's what that is. He's calling the work function phi. Okay, and he wants it written in electron volts. That's what that is. Right here, it's Hf is h lambda over Hc over lambda. That's for energy of a photon. Okay. This here is momentum of a photon. This is the value of H. Okay, and this is a conversion for electron volts. You're basically dividing by the charge on electron. Here we're talking about change in energy, not really necessary. This is the same equation for the most part. This right here, that's for diffraction, finding the wavelength based off the energy levels of an electron. It's pretty much the same equation I would use, except for I would have an F here and an I here, because sometimes you don't go to the second energy level or the first excited state. Sometimes you go to other states, so I just have an F and N squared. That is the Rydberg constant. When we get here, we're starting to get into the Bohr model. So let me switch colors of pens. This right here, this is the Bohr model right here, and this is the radius of the Bohr model. Okay, so right there we have the Bohr model of the atom. I'm trying to see if there's anything else we need in this. Yeah, all of this is the Bohr model of the atom. Okay, it's a little bit different what I'm used to, and it's out of order because the Bohr model atom should be down here with the quantum model. This down here is the quantum model. All right, so there's that. The stuff in the middle, this is Compton scattering. That's what this over here is. That's Compton scattering. This right here, it's Heisenberg's uncertainty. And this is de Broglie wavelength. Okay? And that's out of place. It should be up here with this stuff up here. This is the first time I've seen him put things out of place that drastically. Okay? Now when we drop down further on here, we get to radioactive decay, and that's what all this stuff is down here. All of this is radioactive decay. Every last bit of this down here is decay. Here we're going over atomic numbers. There's one important equation here that I didn't outline in radioactive decay. This is the radius of the atom. Not something I go over during the weekly classes, but it's on the test review. Okay? Now we have our conversions for atomic mass units. We have the proton, neutron, and electron masses in atomic mass units. You're going to need those on the test. Here I'm not sure what the H is. I know P and electron. I know what that is. Oh, hydrogen. This is a mass of hydrogen. Over here, we're talking about change in mass and number of protons plus number of nucleons minus, I'm not sure what he's doing there. This equation we really don't need to use, although it's Einstein's. What we should use in its place is delta M 931.5. And he tells you that right here, 1 U is equal 931.5. Okay, I'm not sure what he's doing with that. I mean, Z's the number of protons. I get that. N is the number of neutrons. So this is the change. This is a mass deficit, but he's doing it kind of weird. He's leaving out the electrons, which I know when you look these numbers up on the tables include the mass of an electron, and you notice the mass of electron is much smaller than the mass of a proton and neutron. So it might be why he's ignoring it, but I know sometimes in the past he didn't. Okay, below this line right here is radioactive decay. Here's your unit conversion. Barks, BQs, bark. I'm not sure how to say that word. I know it when I see it. And I think this is Curie's, but I'm not sure. That's just a unit conversion. Don't really use it much. Okay, he calls it the Q reaction here, which really belongs up here more. This is for fusion and energy release. Don't really know it if you know how to work the problems. It's just changing mass times 931.5. That's all you do. You don't need that equation there. Now getting into the radioactive decay. This one right here is activity. This here is PERT. This is the half-life equation. Not half-life. Yeah, it is half-life. And I don't use this way. Neither of these do I really use that way. Here's what I use in their place. I do half-life is, sorry, not that. I do my decay rate is the ln of 1/2 over the half-life. So this time the way I do the equations is very, very different from what he's doing. Very, very different. And I hope this helps you all a little bit. And I just noticed I was zoomed in a little too much down here. But I hope this helps you all. You get to see the equation sheet and walk through where everything is. And I hope you enjoyed the video. Thanks.